So please make sure that you are filling in correct answers along the way. Yesterday we were looking at physical changes and how that affects different properties. So we talked about freezing and melting. Number one, a physical change that occurs when a material goes from solid to a liquid. From a solid to a liquid. What is that called? What is that called? Adriana? Melting. Melting, yes. Number two, a change in some properties of matter without forming a different kind of matter. Alexis, that's a physical change, yes. And number three, a physical change that occurs when a material goes from a liquid to a solid, a liquid to a solid, a liquid to a solid. Xavier? Freezing, yes, yes. So you want to make sure that you understand those different vocabulary words. I'm assuming you've been practicing on your Quizlet with some of the vocabulary there, okay? Now, number four, you're to determine if the statement is true or false and then explain your choice. A physical change occurs when matter changes state as from a liquid to a gas. True or false? How many of you had true? True. That statement is true. That statement is true. Okay? It's true because just changing the state does not alter the basic material. All right? So, when we talk about the different state of it, okay? We used water, and we talked about water could be in the form of a solid, a liquid, a gas, right? Okay? You can melt it, it's still water. You can freeze it, it's still water, it's just solid now. You can change it to steam, but it's still a form of water, right? All of those are water. It just changes the form that it's in, but it's still the basic material, all right? Now, what? Yes, no, you correct it. You correct it. Okay. Changing the state does not alter the material. Okay? So it's still H2O. Does that make sense? Doesn't matter what form it's in, it's still H2O. All right, now, number five. Changing a ball of bread dough into a loaf. A ball into a loaf. You know what a loaf looks like, right? A ball into a loaf. Changes the shape and mass of the dough, but not its color. How many of you had true for that one? How many of you had false? That is false. Think about that. Think about that one. When we talk about that one, we went from a ball, right, into a loaf, right? Okay? Into a loaf, okay? All right? It changed the shape, right? Yeah. Okay? Did it change the mass? No. No, all we did was change the shape. It didn't say we added dough to it, we took away dough, so it still weighed the same. So let's say if this was 12 ounces, this also was going to be 12 ounces, right?
It's a happy face.
All right? Oh. So the mass is the same, okay? Shaping a ball of bread dough into loaf changes the shape and mass of the dough, but not its color. That would have to be false, right? Because both the mass and the color stay the same.
But just the volume.
Did the volume change?
Yeah.
No. No. Did the amount of matter change? No. If we did this, if we had a big tub that had water in it, right?
Yeah.
And we had another tub, same size, that had the same amount of water in it. Okay? If we put the ball of dough in it, or we put the loaf of dough in it, right? Would the water rise up to the same amount?
Yes.
Yes. Because I put the same amount of matter in it, right? Okay? Does that make sense? That would be like saying, I jumped in standing like this, or I jumped in standing like this. Did my weight change? No. I didn't lose any weight by bending over, did I?
You're just staying.
Okay? Does that make sense?
Yeah.
Okay? Did my color change?
No.
No. Okay? All right? So that one is false because shaping it into a loaf might change its shape, right? But it didn't change its mass,
Won't matter.
and it didn't change its color, right? Okay? Now, number 6. When you put honey in the refrigerator, it eventually turns to a solid.
Yeah.
How many of you experienced that?
Yeah, we put it in.
Okay? What would you do to turn it back into a liquid? Winnie,
Take it out of the fridge. Put it in the.
take it out of the
Put it on
fridge.
top of.
Sophia, shh.
Freeze it and then put it in the microwave after on the stove.
Okay? Leave it in the sun.
Hold it like over it. Hold it like over it.
Okay?
Heat it up.
All right?
Flamethrower.
What?
Flamethrower, but don't burn it too much.
Okay? All right? So any questions on physical change? Physical change. Some other things we talked about the other day. We took that piece of paper and we did several things to it. Look in your notebook at how many different words we used for physical change. Did we put down freezing and melting with our physical changes? Did we add that to our list?
Yes. Yes.
Okay?
Yeah. You can freeze the paper, but then you can make it disappear.
I don't think you can freeze paper.
Yeah, you can. You set it. You pour some water on it. Set it in the freezer.
Okay.
Then it freeze.
Yeah, and then you just crack it. You know, I.
All right. So are we good with that? Okay. Read through your notes. Refresh yourself on the things you've already studied.
So if I take a piece of paper and I light it, hold it,
Okay, do you have questions on physical change? Physical change, yes.
I don't think this would be physical change, but what happens if you electrocute, like a paper or whatever? What, like, and it, like, it disintegrates, is that physical change?
No, that becomes a chemical change. Okay.
Lightning, chemical.
All right. So here we go. Today we're going to talk about chemical change. Chemical change. Okay. Chemical change. So in your notes, we need to start a section on chemical change. Chemical change.
You just said Kim Kardashian. Kardashian change. We're all gonna change it.
I don't like it.
Ricky, we're taking notes. You should be too. One or more types of matter change into other types of matter with different properties. Do a quick one. So in a physical change, we still recognize it as the same, right? Okay. In a chemical change, it changes into another type of matter. All right? Does that make sense?
Yeah.
Okay. So, for example, have any of you ever seen anything called rust?
Yes. Yeah.
Rust. Okay. Rust is a familiar chemical change. Okay. So let's list that as one example. Okay. Rust. Okay, that's an example of a chemical change. A change has taken place with iron. Does that make sense? It no longer has the same makeup, right? Okay, it doesn't look the same as it started out as. Okay? Does that make sense? Okay. That rust is now red and it's brittle. Okay? The iron before that usually is smooth, right? And it usually is not that orangish red color. Okay? All right? When you think of a vehicle that gets rusty, okay? It becomes brittle, okay? Changes color, whatever the original color of the vehicle was, it's no longer that color, and it gets brittle. It has changed into other types of matter with different properties. Okay? All right? That's called a chemical change. All right? Does that make sense? We're going to talk about some more chemical changes here. Yes? Rust happens because of chemical reactions to the iron. Does that make sense? All right? So when you leave iron out in the water, all right, the reaction of the water to the iron is what creates, like I left a little red wagon out. That's metal. Okay? It doesn't like getting wet. So the chemical reaction to that is it gets rusty. Does that make sense? That's a very simplistic little explanation. There's a whole lot more to it than that, but we don't have enough science behind us to like get into all that. Does that make sense? Okay? All right? Okay? How many of you have boiled an egg before? Okay? Think about if you had cracked open a raw egg, what it looks like. Okay? Now it's boiled, and you crack it open. Does it look the same?
No.
No. That is a chemical change that has taken place. Does that make sense? Okay? The egg white was runny to begin with. It was clear, right? Now it's a hard substance. It's white. Okay? The yolk, while it's still the same color, it's yellow, but it's a different color of yellow usually. Okay? Might be a brighter yellow. But now it is hard. It's not runny, right? Okay? Does that make sense? Okay? Think about tomatoes. Tomatoes. Chemically, what happens to those? They change what? They change color. As they ripen, they change color and turn to red, usually from green to red, right?
Green, yellow to red.
Okay? All right? That's a chemical change. Okay? Do they change when they ripen or when the egg gets boiled? Do they all of a sudden get redder? No. They change color or they change like the egg gets harder, right? Okay? All right, but it's a chemical change. Okay? So when a tomato reaches its size, it stops growing in size, and then it changes its color. Okay? Does that make sense? That's what I'm talking about. Okay? All right? So, in those chemical changes, the particles that make up the egg or the tomato are rearranged to form the new substance. Okay? We didn't add or take away things. It was rearranged. Does that make sense? So it wasn't like somebody came up to that egg and gave it a little shot to make it different. Alright? It wasn't like somebody comes up to every tomato and gives it a shot of something to make it different. Or sprinkles something over it to make it red. Okay? It's that the substances within it are rearranged to make it different. It is called a chemical change. Alright? Yes, Bruce.
Also, you need to water tomatoes every single day.
You what?
You have to water tomatoes.
Pretty frequently, yes. Okay? Alright?
It doesn't make them change their color.
Actually, you have to.
Now, some chemical changes can change, like the volume of something. Have any of you ever made bread?
No.
Okay? Bread is a little different than muffins. Okay?
Yeah, bread.
When you make bread, have you ever kneaded bread by hand?
No.
And then you set it in the bowl and you let it what?
Right.
Rise. The chemical change allows for the bread to rise. Alright? Okay, so that chemical change can cause for the gases within it to cause the bread to rise. Does anybody know what ingredient helps it rise?
Yeah. The weird little things.
The weird little things.
The animals that go in there that
The animals?
Yeah.
No.
Like yeast.
Yeast?
no,
Yeast. Yeah, that's not an animal, so.
And how my mom called them little bees or whatever that eat like
It's called yeast.
stuff.
It's called yeast, okay? All right? All right?
He's little messed up.
Okay? All right. So, what was this? That is a chemical change there.
So let's write down a couple more examples here.
It might be.
Oh my goodness. Ripening fruit would be an example. Boiling egg.
Yeast is an animal.
You taking notes?
I don't look at Instagram the same way. Little animal now. That's pretty.
It's a little yeast animal. It's a yeast.
It's a yeast.
It's a boo. It's a boo. That's funny. It's a boo.
Do you mean boiled egg instead of boiling?
Boiling an egg. I should have an egg. Yeah. There we go.
It's a yeast.
All right. So, if we measure the weight or the mass of gases and smoke, all right? Do you remember the balloon?
Yeah, it's called
Okay. All right. No.
It's stuff with
If we measure the weight or the mass of gases, guys, measuring the weight or the mass of gases and smoke is tricky. For many centuries, people did not even realize that smoke and gas have mass because they felt like it just disappeared, right? Disappeared into the air, okay? The law of conservation of mass can be confirmed by observing chemical changes in sealed containers that do not allow matter to get in or out. Do you remember the video clip where they contained all that? And they proved that even though there was gas in there, it was still, the mass did not change. You remember that?
Yeah,
Okay.
that's actually cool.
So if you place a piece of wood inside a closed container with enough air to let it burn completely, you will find that the total weight of the container and its contents is the same before and after burning. Okay? Mass is conserved even if the volume of the products of a chemical change is very different from the volume of the original substance. Did you hear that?
Yeah.
Okay, I'll read it again. Mass is conserved even if the volume of the products of a chemical change is very different from the volume of the original substance. Conservation of mass, right? Okay? All right? Matter is not created or destroyed in chemical changes. It's only changing forms. Okay? So, we can have those chemical changes, but is the mass going to change? No. All right? I'm going to walk you through an experiment next. Those of you at home should be able to bring up the lab sheet.
Down. Everybody in here for mouth. When it goes mouth.
Mass. I think you don't know how to say that out. Mass.
Mouth?
You say mouth.
When you cook a mouth, it tastes mouth. Cook a mouse. It tastes mouth.
Ricky and Bruce,
When you take
unless you're burning, luncheon now. Yeah.
You think it's good for your head and it burns you, know?
And that's what
If everybody did not get a lab sheet, oops, sorry. I always ask them if they're gonna walk around. All right, those of you at home, did you find the lab sheet? It says Phys Lab at the top. Did it not get to you? Oh dear.
Murderous pencil. Sharpen the lady. And sharpen the
Did you see the eraser off or juice?
Hey,
You did. How did she get it? That was not like that at the time.
No, he said he was sharpening. And my one was sharpening. Even I don't have to silver bladed.
Okay, those of you should see, get your name written on your Phys Lab.
Look at Ricky. He was like this. Look at Hurry, look.
Ricky? Bruce?
He's making fun of blood.
No.
I have no.
No.
No,
Quit.
he's making fun of blood. Remember that one.
No, I don't.
Is that one of the last one?
You don't want to around. Or you ever know doing. You're good.
It's like this.
All right, should be there now, guys. Sorry, I thought it was already there. Just like this. Find it? Thank you, Lily. All right, for this one, we're going to use cold water and warm water. We're going to use fizz tabs. We're going to be timing how long it takes the fizz tabs to last in the water. Okay? We're going to have the same amount of cold water as we do warm water. We're going to have the same type of fizz tabs in each one, which when you do experiments, you eliminate all things that you can that would be different. Does that make sense? Like I don't use two different brands of fizz tabs in case there's something different about them that might cause different outcomes.
Like,
Okay?
I don't want to put it in the freezer.
We'll keep track of the time that the tablets fizz, all right? And we'll be recording that. Now, at the top of your paper, I want you to make a prediction at the very top, At the very top of your paper. The very top, that'd be up here. This is the top of your paper, folks.
By your name?
Above your name, above everything, clear at the top. I want you to make a prediction. Do you think the fizz tabs will go longer in cold water or warm water? Just write cold or warm. Which one do you think it will go longer in? Cold or warm? Comma. Do you think the mass of the water will be different? Do you think the mass of the water will be different before or after, like we do the fizz? You know, it fizzes. Do you think it should be different? Different or the same, so you can write down different or same for mass. So make sure you put mass with that one so you know you're talking about the mass. And then comma. And do you think the volume will change after the tablets are done fizzing? The volume. Do you think the volume of the water will change? So on your lab sheets, do you see where it says mass, cold water, warm water, fizz tab? We're in the first column on before.
Yeah.
The fizz tabs are 6 and 5/10 grams. 6 and 5/10 grams. So please record that on your lab sheet. Fizz tab. Find it in the first column. Fizz tab, 6 and 5/10 grams. Now I double checked, they are both the same, which means that when they were manufactured, they are making sure when they manufacture them, they are the same. Okay?
So it won't matter. It won't go off like the warm water and the cold water one. There's no discrepancies there. Does that make sense? Okay? Now the next thing we're going to have to do is find the mass of our 100 milliliters of water. I've got our warm water in one. Our cold water in the other. I made sure they were identical. Because if they are not identical in the volume, that can throw our experiment off. The warm water mass, do you see where we are in the before? Warm water, 120 and 8/10. Please write that down. 120 and 8/10. Warm water mass, 120.8.
What, 40.8?
Yes. Now,
Oh, right under here.
yeah. Now, in theory, if I could eyeball this exactly, the cold water would be exactly the same, but I'm eyeballing it, okay? The cold water is 121.1. Not bad for eyeballing, pretty close, okay?
I knew the volume would be the same.
The cold. The cold. So for eyeballing, that was pretty darn good.
Yeah, it was.
And our tablets were what again? 6 and 5/10. Okay. Now, I'm going to drop the fizz tabs in at the exact same time. Okay? And that's important to know. Okay? No, the cold water was 121.1. While I tried to eyeball it exactly the same, that's very hard to do. Does that make sense? Okay? All right, I'm going to drop them in at the exact same time. They're going to fizz, and I'm going to set them here and here. This part of the room, tell me when this one stops. This part of the room, tell me when that one stops. Here we go. I dropped them. They're fizzing.
That was like,
No. Just tell me when it stopped fizzing. Which one has?
this side.
This side stopped fizzing at 38 seconds.
Was that the warm water?
Is anybody watching this one? It stopped at 49 seconds. Just a minute. Okay. So, down at the very bottom, how long did the tablets fizz? The cold was 49 seconds. The warm was 38 seconds. Those of you at home, are you getting that down on your lab sheets? Any sign from home that anybody's getting it? Hello? Somebody, give me a sign from home that you're getting that. Thank you. Thank you. Sometimes I feel like I'm only talking to my computer and nothing else. Thank you. All right.
Now, first off, let's look at our prediction. How many of you in your prediction thought that the fizz tablets would last longer in the cold water? You guys at home? Anybody? Last longer in the cold water. Okay. Caleb and Hayden, I don't see you. All right. Then your prediction was correct. You did the experiment, it was correct. Okay? All right? Now, when we look at the volume of the cold, the volume of the cold, I may have to use
It will go all the way to the top of it.
over there. What do you say? It should have come immediately. Yeah, a little over 100.
Whoa.
Okay, just a tad. So I'm not sure if it's the inaccuracy of, like, I didn't get it exactly on 100 there or not. So we'll wait a second here. I will weigh it. 123 and 5/10 for the cold. 123 and 5/10. And we're going to talk about this in a minute. Okay. The after, the mass is 123 and 5/10 for the cold. For the warm, it's 126 and 0/10.
So 123.5.
So for the cold, the mass was 123 and 5/10, and the warm was 126 and 0/10.
What was the third one again?
123 and 5/10. Okay?
And what's the other one?
126 and 0/10. Okay. So let's see.
Wow. I didn't realize it went down. How did it go down?
It went down
Yeah. It was 128.
120 and 8/10. 120.8.
That looks like spring. Oh, I just want.
I know.
It went up.
So yeah, that was also more. Okay. All right. But again, it could have been my eyeballing it, right? Okay. All right. Let's talk about the mass. The mass would have been the water in the fizz tab, right? And what happened when it bubbled? 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 What? Okay. And what happened to the tabs? They turned into a what? What form? turn into? Okay, what form did they turn into? Nope,
Gas.
not liquid,
Gas.
a gas. Did we contain the gas?
No.
No. Had we contained the gas in here, what would we have found the mass to be?
Way more.
It would have been more and also dissolved.
If we had contained the gas, right, our mass would have been the same as adding the water and the fizz tabs together, right? So what did we let the gas do?
We let it.
We let it go out into the space of our room, right?
Which is Earth.
Right? Because remember, look back at our pictures. Gas takes the shape of the container. Our container for our gas was the room. Right? We did not contain the gas in our container, right? We let the gas escape. So our mass was going to be less than the water plus the fizz tabs because we let the gas escape. Does that make sense? Does that make sense? If we had a lid on this, and none of the bubbles of gas, okay, could have escaped, then our mass would have been the same. Does everybody understand that? Questions on that? Anybody? So again, the law of conservation of mass. Law of conservation of mass. Okay? Now, in this chemical change, in this particular case, the warm water sped up the chemical change of the fizz tabs, right? So, we've discovered that in this particular experiment, a chemical change took place by the temperature of the water. It changed how that experiment would happen, how those fizz tabs would react. Does that make sense? Okay? Questions? Law of conservation of mass. Do you understand it? Okay? Do you understand why the mass was not the same this time in our experiment?
Yeah.
We allowed for the gases to escape. Had we covered it, then it would have all stayed in there and our mass would have been
Way higher.
the same. The same as just adding the water and the fizz tabs together. Does that make sense? Okay? But I didn't put a lid on it. I let the gases escape. Okay?
Yeah.
All right. Questions from home? Anybody? Okay, so we worked on chemical change today. All right? We've had physical change and we worked on chemical change today. You've got some time now. Go into your Quizlet and work on your vocabulary. Not the solar system, no.
I'm trying to keep the camera.
Bruh. The kid, man.
I know.